Newton's third law, action, reaction. The big idea. For every force, there is an equal and opposite force. A force is always part of a mutual action that involves another force. In the simplest sense, a force is a push or a pull. A mutual action is an interaction between one thing and another. For every push or pull, there is an opposite returning push or pull. When you push on the wall pushes on you. The reason for this is that if you were to push on a wall and the wall did not push back, you would push through the wall. In order for the wall to hold you up, it has to exert an equal but opposite force upon you to hold you up. Likewise, the interaction that drives the nail is the same as the one that halts the hammer. You slam the hammer down upon the head of the nail moves, resisting somewhat, until it is buried deeper into the wood. What stops the whole process is the resisting force upwards to stop the hammer. If there was no resistance, if there was no force upwards to equal that hammer, then the hammer would simply pass right through the nail, the board, and everything else. Hammer exerts a force on the nail and drives it into a board. There must be a force exerted on the hammer to halt it. Newton reasoned that while the hammer exerts a force on the nail must exert a force back on the hammer. In the interaction, there are a pair of forces, one acting on the nail and the other acting on the hammer. This is the mutual interaction. Question: does a stick of dynamite contain force? If yes or no, explain. The answer is no. Force is not something an object has, like mass. Force is an interaction between one object and another. An object may possess the capability of exerting a force on another object, but it cannot possess force as a thing in and of itself. Later we will see that something like a stick of dynamite possesses energy, which is related to the capability of force. But remember, force is not something that you measure, like temperature, or length, or location in a room. It is not a property intrinsic to anything. It is an interaction. Why do forces always occur in pairs? Newton's third law states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. Newton's third law describes the relationship between two forces in an interaction. One force is called the action force. The other force is called the reaction force. Neither force exists without the other. They are equal in strength and opposite in direction. They occur at the same time simultaneously. Think back to the example of the hammer striking the nail. The action force would be the hammer hitting the nail. The reaction force is the nail pushing back upon the hammer. The nail cannot press upwards on the hammer unless the hammer presses downward on the nail. Newton's third law is often stated: to every action there is always an equal opposing reaction, or for every action there is an equal and opposite reaction. It doesn't matter which force we call action and which we call reaction. These are simply markers to let us know what the initiating force is. typically used to call the actions things like the swing of the hammer or pressing upon the wall. But in reality, it's simply two forces, a pair of forces, and how we name them, action and reaction, is largely a matter of perspective. In every interaction, the forces always occur in pairs. You push against the floor simultaneously pushes against you, lest you fall through. The tires of a car interact with the road to produce the car's motion. The tires push against the road, and the road simultaneously pushes back upon the tires. When swimming, you push the water backward, and the water pushes you forward. The interactions in these examples depend upon friction. A person trying to walk on ice, where friction is minimal, may not be able to exert an action force against the ice. Without the action force, there cannot be a reaction force, and thus there is no resulting forward motion. This can easily be applied to the car and the tire example with the road. When there is slick oil or water after a fresh rain on the road, there is typically less friction, and thus it is easier to lose control of your vehicle because of the decreased friction, therefore decreased action force, and decreased reaction force. When the girl jumps to shore, the boat moves backwards. Typically, this results in a comic situation where she simply falls right into the water, or, given the position of this particular cartoon, likely falls feet first in the water but head first into the dock. The dog wags the tail, and the tail wags the dog. Interesting concept that the tail is not actually moving the dog, but for the dog to move his tail, the tail has to be responding back towards the dog. And in some breeds of dogs, you can see how the tail is in fact wagging the dog, given that they are wagging so hard that their entire hips are moving back and forth. What happens when an object exerts a force on another object? To identify a pair of action-reaction forces, first identify the interacting objects A and B. And if the action is A on B, the reaction is B on A. If using the letters A and B prove difficult in understanding the concept, feel free to replace these with any of the examples we've given thus far, with A being the hammer and B being the nail, or A being the tire, B being the road. There is a simple recipe for treating action and reaction forces. First, identify the interaction. Let's say one object, A, interacts with another object, B. The action and reaction forces are stated in the form action, object A exerts a force on object B, and reaction, object B exerts a force on object A. Sometimes the identity of the pair of action and reaction forces in an interaction is not immediately obvious. For example, what are the action and reaction forces in the case of a falling boulder? In this case, if we call the action Earth exerting a force on the boulder, then the reaction is the boulder simultaneously exerting a force upon the Earth. When action is A exerts force on B, the reaction is simply B exerts force on A. So in all of these examples, it shows that the action is the tire pressing on the road, or rocket pushing on gas, or the earth pulls the ball. For the reactions, we should simply flip these statements as such. tire pushes on road becomes road pushes on tire for the reaction. For the rocket, rocket pushes on the gas for the action. The reaction is the gas pushes the rocket. And finally, if Earth pulls the ball, then the reaction is the ball pulls the Earth. So, we know that Earth pulls on the Moon. Does the Moon also pull on the Earth? If so, which pull is stronger? Answer. Asking which pull is stronger is like asking which distance is greater between New York and San Francisco or between San Francisco and New York. The distances either way are in fact the same. It is the same with force pairs. Both Earth and Moon pull on each other with equal and opposite forces. If this seems odd because of the relative size of Earth to Moon, Moon to Earth, if one was pulling harder than the other, then the distances between the Moon and the Earth would close. If the Moon pulled us harder than we pulled it, we would be drifting towards the Moon. And, likewise, if the Earth pulled harder than the Moon, then the Moon would be slowly but surely crashing into the planet. Since that's yet to occur, then thankfully, these are an equal and opposite force pair. How do you identify the action-reaction forces in an interaction? A given force exerted on a small mass produces a greater acceleration than the same force exerted on a large mass. Earth is pulled up by the boulder with just as much force as the boulder is pulled down by Earth. In the interaction between the boulder and Earth, the boulder pulls up on Earth with as much force as Earth pulls down on the boulder. The forces are equal in strength and opposite in direction. The boulder falls to Earth and the Earth falls to the boulder, but the distance Earth falls is much less. Although the pair of forces between the boulder and Earth is the same, the masses are quite unequal. Acceleration is not only proportional to the net force, or total force, but it is also inversely proportional to mass, or, as mass is larger, acceleration goes down, as mass is smaller, acceleration goes up. Because Earth has a huge mass, we don't sense its infinitesimally small acceleration. When a cannon is fired, there is an interaction between the cannon and the cannonball. The force the cannon exerts on the cannonball is exactly equal and opposite to the force the cannonball exerts on the cannon. You might expect the cannon to kick more than it does. The cannonball moves so fast compared with the cannon. According to Newton's second law, we must also consider the masses. It should go without saying that the cannon and the cannonball have significantly different masses. The cannonball undergoes more acceleration than the cannon because its mass is so much smaller. According to the diagram, the cannon will roll backwards due to the equal but opposite force that we've just learned, but the cannonball will propel forward tremendously faster due to being much, much smaller in total mass. F represents both the action and reaction forces. M, the mass of the cannon, and m, the mass of the cannonball, as you can see written below. You see why the change in the velocity of the cannonball is greater compared to the change in the velocity of the cannon? F remains the same. However, due to the formula, the algebra before you, a small m produces a large A, and a large M produces a small a. We can extend the basic idea of a cannon recoiling from the cannonball it launches to understand rocket propulsion. The balloon recoils from the escaping air and climbs upward. If a balloon is released and allowed to move, it accelerates as the air comes out. A rocket accelerates in much the same way. It continually recoils from the exhaust gases ejected from its engines. Each molecule of exhaust gas acts like a tiny molecular cannonball shot downward from the rocket. A common misconception is that a rocket is propelled by the impact of exhaust gases against the atmosphere. Both the rocket and recoiling cannon accelerate because of the reaction forces created by the, quote, cannonballs they fire, air or no air. In fact, rockets work better above the atmosphere where there is no air resistance at all. If in fact we needed a backdrop of atmosphere or the Earth itself in order for a rocket to take off, rockets would cease to work almost entirely in deep space, where there is little to no molecules in the area at all. Again, the rocket recoils from the molecular cannonballs, the mass of each of those molecules. It fires and climbs upward. Lift. Using Newton's third law, we can understand how a helicopter gets its lifting force. The whirling blades force air particles downward. This is the action. The air forces the blades upward. Reaction. This upward reaction force is called lift. When lift equals the weight of the craft, the helicopter hovers in midair. When lift is greater, the helicopter climbs upward. And obviously, if lift is less than the weight, the helicopter descends or crashes. Birds and airplanes also fly because of action and reaction forces. When a bird is soaring, the shape of its wings deflects air downward. The air in turn pushes the bird upward. The slightly tilted wings of an airplane also deflect oncoming air downward and produce lift. An interesting story behind the wings of airplanes. Airplane wings for the longest time were designed completely flat, and with the original Wright brothers designing these planes and those that followed after them, they didn't get much lift. The curvature of the wings that were later made were done so due to observations of actual birds and the curvature of their wings. Pressure changes is what accounts for this upward lifting force. Think. A tug of war occurs between boys and girls on a polished floor that's somewhat slippery. If the boys are wearing socks and the girls are wearing rubber-soled shoes, who will surely win, and why? Answer: the girls will win. The force of friction is greater between the girls' feet and the floor than between the boys' feet and the floor. When both the boys and the girls exert action forces on the floor exerts a greater reaction force on the girls' feet. The girls stay at rest, and the boys slide towards the girls. This would be true if the boys and girls swapped footwear as well, because this has little to do with strength and has all to do with the interaction between the contact of their feet and the floor. Why do objects that experience the same amount of force accelerate at different rates? Action and reaction forces do not cancel each other when either of the forces is external to the system being considered. Since action and reaction forces are equal and opposite, why don't they cancel to zero? To answer this question, we must consider the system involved. Remember, a system is whatever we define it to be with particular boundaries. So a system can be merely everything inside of a box, or a small home, or the entirety of the planet, or the entirety of the solar system, or beyond, or anything in between. So systems are defined by their boundaries. A force acts on the orange, and the orange accelerates to the right. The dashed line surrounding the orange encloses and defines the system. The vector that pokes outside the dashed line represents an external force on the system. The system, that is, the orange, accelerates in accord with Newton's second law. The force on the orange provided by the apple is not cancelled by the reaction force on the apple. The orange still accelerates. The force is provided by an apple, which doesn't change our analysis. The apple is outside of our defined system. The fact that the orange simultaneously exerts a force on the apple, which is external to the system, may affect the apple, which would be another system if we defined it, but not the orange. You can't cancel a force on the orange with a force on the apple. So in this case, the action and reaction forces do not cancel. Action and reaction forces cancel. As you can see, the dotted line surrounds both the apple and the orange. When the floor pushes on the apple, reaction of the apple's push on the floor, and the orange apple system accelerates. When the force pair is internal to the orange apple system, the forces do cancel each other. They play no role in accelerating the system. A force external to the system is needed for acceleration. When the apple pushes against the floor simultaneously pushes on the apple, an external force on the system. The system accelerates to the right. Inside a baseball, trillions of interatomic forces hold the ball together but play no role in accelerating the ball. They are part of action-reaction pairs within the ball, but they combine to zero. If the action-reaction forces are internal to the system, then they cancel and the system does not accelerate. A force external to the ball, such as a swinging bat provides, is needed to accelerate the ball. To put this another way, the ball is made up of molecular forces that are holding together, bouncing around, vibrating, interacting with each other in order to produce the texture, the material, the hardness, the softness, etc. of that baseball. However, all of those sum up to one big fat zero in terms of force, because the ball does not spontaneously move to the left or the right. These forces don't cause that. It requires an external force to the system of the baseball in order to move that system, the baseball, anywhere. Another example, a football is kicked. Force A acts on object B, and B accelerates. However, both A and C act on B, and they can potentially cancel each other, so B does not accelerate. The example is a bit odd given that you typically do not have two people kicking a football at the same time. This would have been better served with perhaps a soccer ball. Most notable when you see the little kids go to kick the ball at the same time because they're all in a big grape cluster, and then the ball goes nowhere while they keep pounding at it. When there is one interaction between the foot and the football, the ball accelerates. If two kicks on the ball are simultaneous, equal, and opposite, then the net force on the ball is zero. Remember, force is in fact a vector, so all of those previous adjectives must hold. They have to be simultaneous, meaning at the same instance in time. They must be equal. The magnitude of the vectors must be equal. And the direction of the vectors have to be opposite of one another. Any of those things differently would cause a net acceleration on the ball. The opposing forces act on the same object, not on different objects, so they do not make up an action-reaction pair. This would be, if to put it another way, the hammer striking the nail pushes back on the hammer. An example of 2 feet kicking the ball, this would be as if you and another carpenter, intelligently enough, decided to strike the same nail with 2 different hammers. Even if they manage to cancel each other out, that is not an action-reaction pair because they're both external forces to the system. Think. Suppose a friend who hears about Newton's third law says that you can't move a football by kicking it because the reaction force by the kicked ball would be equal and opposite to your kicking force. The net force would be zero, so no matter how hard you kick, the ball won't move. What do you say to your friend? Be nice. Answer. If you kick a football, it absolutely will accelerate. No other force has been applied to the ball. Tell your friend that you can't cancel a force on the ball with a force on your foot. Why don't action-reaction forces cancel one another? The horse-cart problem. If the horse in the horse-cart system pushes the ground with a greater force than it pulls on the cart, there is a net force on the horse, and the horse-cart system accelerates. Here's our horse and cart. All the pairs of forces that act on the horse and cart are shown. The acceleration of the horse-cart system is due to the net force of large F minus small f. Will the horse's pull on the cart be cancelled by the opposite and equal pull by the cart on the horse, thus making acceleration impossible? From the farmer's point of view, the only concern is with the force exerted on the cart system. The net force on the cart divided by the mass of the cart is the acceleration. The farmer doesn't care about the reaction on the horse. Now look at just the horse system. The opposite reaction force by the cart on the horse restrains the horse. Without this force, the horse could freely gallop to the market. However, the horse moves forward by interacting with the ground. When the horse pushes backward on the ground simultaneously pushes forward on the horse. Look at the horse-cart system as a whole. The pull of the horse on the cart and the reaction of the cart on the horse are internal forces within the system. They contribute nothing to the acceleration of the horse-cart system. They cancel and can be completely neglected or ignored. Think back to when we were describing the baseball. There are intermolecular and internal forces that hold a baseball together, but they have no bearing on how fast or slow a baseball travels when struck by a baseball bat, because they are internal to the baseball system. To move across the ground, there must be an interaction between the horse-cart system and the ground. It is the outside reaction by the ground that pushes that system. Think, what is the net force that acts on the cart, on the horse, on the ground? Answer, the net force on the cart is going to be P minus F. On the horse, F minus P. On the ground, large F minus little f. How does a horse cart system accelerate? For every interaction between things, there is always a pair of oppositely directed forces that are equal in strength. If you hit the wall, it will hit you equally hard. If a sheet of paper is held in midair, the heavyweight champion of the world could not strike the paper with a force of 200 newtons. The paper is simply not capable of exerting a reaction force of 200 newtons, and you cannot have an action force without a reaction force. If the paper was against the wall, then the wall will easily assist the paper in providing 200 newtons of reaction force, and more if needed. To put another way, if this is a difficult concept to get in your head, imagine swinging as hard as you can a child's play t-ball bat, one of those flimsy, thin plastic things that is mostly air and is designed for, say, a 3-year-old to practice their baseball skills. Imagine smacking someone in the back of the head with one of those as hard as you can. At best, you're going to get a mild thump, because the bat simply does not have the necessary properties to maintain a high amount of force. However, take that same amount of acceleration with something with a lot more mass, like a real baseball bat, and smack someone in the back of the head with the same amount of acceleration, and you'll have quite a dramatic change in reaction and action. If you push hard on the world, for example, the world pushes hard on you. If you touch the world gently, the world will touch gently in return. You cannot touch without being touched. Newton's third law. What must occur in every interaction between any two things?